Today we will discuss the modern electron cloud model, which is also called the quantum mechanical model. Although many of the basic ideas of the Bohr atomic model still hold true, scientists now know that the electrons do not actually orbit the nucleus as in the planetary model. If we connect the dots below, we can see this cloud model, which is the current model of the atom. We've gone through several stages of development of the atomic model theory. This is the currently accurate model. This is called the quantum mechanical or the modern electron cloud model. So if you do the connect the dots below, start at number 1 to 2 to 3 to 4 to 5, 6, 7, 8, 9, and I'll go all the way to 10 with you. If you continue it, you can see it starts to already fill in. Well, we call this the electron cloud model. This is how we describe atoms today. Electrons dart about in a constantly changing path. And that path forms a region called the electron cloud. A visual for this would be the blades of a fan. They're moving so quickly you can't actually distinguish each blade in the fan. And instead you see a blur. When you finish your connect the dots, you'll see the blur. So they act more like an energy wave than like a tiny particle. So we've been talking about these wavelengths and the way that the electrons produce them. Well, these electrons themselves act more like a wave. And because of this, we can only find the probable location of an electron, not the exact location. So like in the Bohr model, electrons are going to be arranged in energy levels within the electron cloud. Those electrons are subject to the laws of quantum mechanics, which means that the electrons carry only certain quantities of energies. These strengths define the energy levels. We've discussed before that at the lowest energy level, that's where our electrons are, closest to the nucleus. And at the highest energy, they're furthest away. We can further break down an energy level into sublevels and orbitals. And we'll talk more about those sublevels and orbitals very soon when we write their electron configurations in just a couple pages. So what does this all mean? What does an atom really look like? Well, an atom has a nucleus of protons and neutrons surrounded by electrons. Those electrons are often pictured as circling the nucleus like planets orbiting the sun. That's the Bohr model. While this picture is useful, it's not very realistic. In reality, the position of an electron is known only as a cloud of probability, and that's what we call an orbital. Orbitals have wondrous shapes, and they're described by Schrödinger's wave equation. We're going to talk about Schrödinger on the next page. Only 2 electrons are allowed to occupy each orbital, so atoms have many electrons with many different overlapping orbitals. Orbitals are grouped into shells and subshells, and the smaller shells are surrounded and permeated by the larger shells, and we have a way of mapping all of these electrons. That's going to be called the electron configuration. An orbital may be pictured as a probability density distribution, which is a fuzzy cloud. So each of these darker regions, the darker it is, the more likely you are to find an electron there. Another way we can show this is using a constant probability, which is more of a bulgy blob. That's this. One is better at showing the reality of where the electrons are, and the other one is better at showing the three-dimensional structure. So you can see what these wondrous shapes I was talking about were. The early part of the 20th century brought changes that revolutionized how we think about physical reality, especially in the atomic realm. So we brought a lot of changes at the beginning of this 20th century, and especially when we're talking about the atomic realm. Before that time, all descriptions of the behavior of matter had been deterministic, which means that whatever the present set of conditions are, they're going to completely determine the future. Quantum mechanics changed that. This new theory suggested that subatomic particles, meaning electrons, protons, and neutrons, in the present are not completely determined in the future. For example, if I shoot one electron down a path and measure exactly where it lands. Then I send in a second electron down the exact same path under the exact same conditions. It will not necessarily follow the same course and will not end in the same place. It may actually end in a completely different place. This is the entire quantum mechanic theory. There's a lot of complicated thoughts about this, and Schrödinger came up with a very good analogy to try and help people of the 20th century think it through. His analogy allows you to think through when there are two possible outcomes that are both equally probable, the fact that you cannot determine which one is the true fact at that moment. So make sure you read through all of this and answer the questions at the bottom. Show signs of your reading by highlighting, underlining, and annotating, meaning asking questions, defining words that you don't know. Show me that you really read through this and are trying to understand it. This will be part of your homework, and make sure you have it completed by tomorrow. So quantum mechanics, with the help of Schrödinger and many other scientists, have confirmed to us that our electrons do not follow that planetary orbital, which is a much easier way of thinking about the electrons. So instead, we need to have a new way to put locations of where each of our electrons are. So let's break down this electron cloud into each of its constituent parts. So orbitals form a number of bizarre three-dimensional shapes depending on their energy. And these orbitals are held within this electron cloud. So we'll start with the electron cloud. It's the entire area in which electrons exist. So electrons orbit the nucleus. They are a very large part of the volume, but hardly any of the mass. When we take that entire electron cloud, the first thing we're going to do is subdivide it into energy levels. So energy levels are broken up into 7 energy levels. If you look at a periodic table, there are 7 side-to-side periods. Well, that's because your periodic table correlates directly with the design of the elements and the design of their orbitals. So for each energy level, you have one side-to-side period in the periodic table. Electrons in an energy level move with only certain quantities of energy. So electrons with the lowest energy are in the energy levels closest to the nucleus. Once we take these 7 energy levels, we can further divide them again into sublevels and orbitals. So each energy level can be broken down in 1 to 4 sublevels. Some just have one sublevel, which would be an S. Notice all have an S. Some have an S and a P, some have an S, a P, and a D, and only my 6th and 7th have an S, a P, a D, and an F sublevel. So we have S, P, D, and F. We'll look at their locations on the periodic table. Like I said, the periodic table is arranged as a kind of map of where all these electrons are. So if we take these sublevels and we look at their orbitals, our S, P, D, and F, let's look at the number of electrons that can be placed in each one. Each orbital can hold 2 electrons, but each sublevel has multiple orbitals. So an S sublevel only has one orbital and therefore can only hold 2 electrons. This is the actual shape of the S orbital. It's just an orb shape right in the middle. It can hold 2 electrons because it only has one orbital. The P has 3 orbitals, 1, 2, 3. So 3 times 2 would be 6 total electrons. The D sublevel has 5 orbitals, 1, 2, 3, 4, 5, each of which can hold 2 electrons for a total of 5 times 2 is 10 electrons. The F sublevel has 7 orbitals. So if I have 7 orbitals and they're very bizarre shapes, 1, 2, 3, 4, 5, 6, 7, I have 7, each of which holds 2 electrons. That gives me a total of 14 electrons. So if I look at each energy level, my first energy level only has one S orbital, therefore it can only hold 2 electrons. My second energy level has an S and a P. Each S can hold 2, each P can hold 6, so I have a total of 8 possible electrons on the second energy level. Third level is the same. So if you notice, this follows the same general trends as the Bohr model. until we start getting into the 4th, 5th, 6th, and 7th energy levels, which include these d and f orbitals, which allow us to hold a lot more electrons on each of those sublevels. So how do we map these electrons? Well, we use what's called an electron configuration. So if you look at your periodic table can be divided into these blocks. Any element that lands in each one of these blocks has its last electron in this sublevel. So my off-ball principle is going to tell me to start with hydrogen, which is of course the upper leftmost element, and build the configuration one electron at a time. So if we're writing our electron configuration, it's going to be a method of indicating the arrangement of electrons about a nucleus. There are some crucial parts to your electron configuration. First, you have a number that will indicate the energy level. On our periodic table, we have our 7 periods, which represent our 7 energy levels. Our S and our P's follow those trends of 1, 2, 3, 4, 5, 6. Our D's and our F's follow a little bit up further than we would expect. Even though this is the 4th row, this is a 3D. And even though this is the 6th row, this would be a 4F. We'll talk about that more, but as long as you know these numbers, we know what energy level we're discussing. Then we have a letter that's going to indicate the type of orbital. All of these are S's, all of these are P's, D's, and F's. And then finally, we have a superscript, the number on top, which indicates how many electrons are in that orbital. So if I have an electron configuration 1s2, the 1 means I'm on energy level 1. The S means I'm in the s orbital, which is the orange block here. And the 2 means I have 2 electrons in there. 1s, second electron in 1s, would be 1s2, and this tells me that the element is helium. Let's try this for a few other elements. If I wanted to find the electron configuration for nitrogen, which would fall right here on your periodic table, you're going to think of it like giving directions. I want to know where every electron is on the way to nitrogen. We always start with hydrogen. Well, you're going to start at 1s, you're going to go down 2 blocks, then you're going to go to 2s, go down 2 blocks, go to 2p, and go down 3 blocks. So the location of nitrogen is at 2p superscript 3. 2 for being on the 2nd energy level, p for being in the p block, and we go down 3 blocks. If I wanted to find it for fluorine, then once again, 1s2, 2s2, 2p, 1, 2, 3, 4, 5. So my electron configuration for fluorine ends in 2p5. So let's pick one further down. What if we did calcium? Calcium falls here on the periodic table. I would start at hydrogen like always. 1s2, 2s2, 2p, 6 blocks, 3s2, 3p, 6 blocks, 4s2. So my final configuration for calcium ends at 4s2. Now you're going to need to learn to write all of the instructions all the way to that element, but I want you to be able to at least identify exactly where the element is with the final part for now. Another way I simply remember how to do this is I said it's like giving directions. Well, if you think of someone with a Bronx accent giving you directions to get all the way over to copper. We have Cu, and he's in the D block. Well, you're going to start at 1s, and you're going to go down 2 blocks. Then you're going to go to 2s and go down 2 more blocks. Go to 2p, keep going for 6 more blocks. When you're at the end of 2p, you're going to be at 3s. Go to 3s, go 2 more blocks. Go to 3p, go 6 more blocks. 4s, 2 blocks. Now, the roll's going to do something a little bit weird. It's going to go up to 3D. Going to go 3D, and you're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9 blocks. When you are at 3D9, you're at copper. It may seem like a strange way to remember it, but it helps stick in my head. I'll point out one more for you. If I wanted to get all the way down to uranium, which is the 4th block, all the way down in the 5F, you'd have to follow all the way through. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 3d10, 5p6, 6s2, and notice, this chunk of the periodic table was taken out because it would make the periodic table way too long and very difficult to print. So this whole chunk actually falls in between 6s and 5d. So we go 6s2, 4f, 14. Remember, f holds 14. The way to know that is you just count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 blocks in F, therefore F can hold 14 electrons, which we already discussed. Now we're up to 5D, go 10 more. 6P, go 6. 7S, 2. We jump down again. 5F, 1, 2, 3, 4. So uranium would be at 5F4. Tomorrow you'll be playing Battleship using this for your battlefield. You'll place your little battleships like normal along the periodic table, and you need to be able to say your coordinates as electron configurations. So if I wanted to hit copper, I would say copper 3d9. Make sure you understand this concept to be able to apply it to a periodic table. Now for writing out the entire electron configuration. The first step is to determine our total number of electrons, which is of course our atomic number. If we use the Aufbau process, then we're filling the orbitals within the electrons, and we'll start with the lowest energy level, which is of course hydrogen. So we start with our lowest energy orbital, and we move up. We build from the ground upwards. The sum of the superscripts should be equal to the total number of electrons. So for magnesium, its a total electron configuration is 1s2, 2s2, 2p6, 3s2. If I add the superscripts, 2 plus 2 plus 6 plus 2, that gives me 12. Magnesium's atomic number is 12, so I can confirm that all of the electrons have been placed in their exact location within the electron cloud. Come back and answer these 4 questions, and then you'll fill in this table. I know the table seems very large and cumbersome, but you should see the pattern very quickly. I'll do 2 of them with you. How about fluorine? Fluorine has atomic number 9. And if we start all the way with hydrogen, we go 1s2, 2s2, 2p, and this time it doesn't go all the way to 6. Fluorine actually falls at 2p5. Now if you look up at the example I gave you mercury. Mercury falls all the way at 4d10. But if you notice, all of these should be the same for every element all the way through 5s2 if they exist around 5s2. So if you follow the pattern of the elements before until you reach your current element, it'll make your electron configuration very quick. And I'll do one more that's further down on your periodic table. How about gold? Gold has the atomic number 79. Now follow along on the periodic table while I go through this. Gold goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2. Now this is one of those parts. 3d9, We go all the way across 3D, but make sure you follow that pattern. We go 4S2 and then 3D, 10, then back to 4P, 6, 5S2, D jumps again, 4D, 10, back up, 5P, 6, 6S2, and now we're at 6S2. This one makes a very big jump. We got to jump down into the F block. We go to 4F and all the way through, all 14 blocks, 4F, 14. Now we're back at 5D, and we don't go through all 10 blocks. We stop at 5D9. This will be the end of your homework. By the time I come to class tomorrow, you should be complete through page 44. I will go over any questions you have at the very beginning of class, and then we'll start our activity. We also have a Friday quiz tomorrow, so make sure you study for that as well. Be on your best behavior as you work during the rest of the period. You may work quietly with a partner, but that is all. Do not try and work as a big group. I will post helpful links on Edmodo for those of you who still struggle with this concept, and please feel free to send me an Edmodo message or come to tutorials today after school or tomorrow morning if you struggle with this before coming to class tomorrow. Have a good day.